Today's lecture is chapter 1.10 to 1.11 on radioactivity. So radioactivity is discussed in a field of chemistry called nuclear chemistry. So nuclear chemistry is the study of the properties and changes of atomic nuclei. And so a nuclear reaction is a reaction that changes an atomic nucleus. So radioactivity is the spontaneous decay and emission of radiation from an unstable nucleus. And we're going to talk about several different types of radiation today, namely alpha radiation, beta radiation, gamma radiation, and most of this work on radioactivity was discovered by Ernest Rutherford in 1879. So he was the same guy that did the gold foil experiment, which discovered the nucleus. And so when you're talking about radioactivity, typically you talk about a radioisotope, which is a radioactive isotope. So not all isotopes of all sorts of atoms are radioactive. Certain isotopes are more radioactive than another. So for example, carbon-14 undergoes radioactive decay to nitrogen-14 in a process that releases an electron through what's called beta radiation. So if we take a look at the nuclear equation that underlies this nuclear decay, we see carbon-14, so we have our symbol for carbon, and we know from our periodic table we have an atomic number of 6 and we have a mass number of 14. And what we're going to have is a radioactive decay where we are increasing our atomic number up to 7, and we're keeping our mass number at 14. And this process involves the release of an electron. Okay, and we draw that electron as an E for electron, and so our atomic number here we have listed as -1. So that -1, so again this is an electron, so that -1 is really telling us that we have, you can think of that subscript number there as the number of protons. So a positive number is talking about positive numbers of charge. Us having a -1 here means we have a -1 charge, which indicates that we're an electron that has 0 mass. Okay, so what we see here, if we look at our number of protons, electrons, and neutrons here, for carbon we have 6 protons. When you have a number of neutrons, 14 minus 6, we have 8 neutrons. And as a neutral, we have 6 electrons. Going to our nitrogen-14 here, where we have 7 protons. 14 minus 7, we have 7 neutrons. And we have, for a neutral molecule, 7 electrons. And then we look at our electron here has 0 protons, 0 neutrons, and 1 electron. Okay, so what we can see has happened here is that we have a change in our number of protons here, change in our number of neutrons, and change in our number of electrons. And if we take a look, we see a conservation in our atomic number and in our mass number. So our mass numbers here, we start with 14 on our reactant side. 14 plus 0 also equals 14. So we see a no net change in our mass number. And we start with 6 protons here. And then we have 7 protons plus a -1, so 7 minus 1 is equal to 6. So what we see here is, again, for our atomic number, we have a balanced equation. So this radioactivity, what we're seeing is a change in the nucleus that's occurring, and what's happening is we have an overall change in our reaction that is balanced. So when we're talking about different types of radiation, first we'll discuss alpha radiation. So alpha radiation is a stream of particles. And so these particles are repelled by a positive charge. They reduce the atomic number of their source by 2, and they reduce the mass number by 4. And remember that the mass number is the summation of our number of protons plus our number of neutrons. So based on this information, what would an alpha particle be? If it's something that has an atomic number of 2, so that means there's 2 protons, reduces a mass number by 4, so that would mean 2 protons plus 2 neutrons, and it has a positive charge, or meaning that it's repelled by positive and attracted to negative. What that means is you have 2 protons, 2 neutrons. That's actually an alpha particle, which is a helium nucleus. And so that alpha radiation is what you ended up, Rutherford used in his gold foil experiment. And so this is called a heavy radioisotope. And so in looking at this example here, an example is uranium, which undergoes alpha radiation, which releases this alpha particle, also known as a helium nucleus, and it can decay down. That uranium will now decay to thorium. And so if we take a look here, we see a conservation in our mass number. So we go 283 on the reactant side is equal to 234 plus 4. And we can see that our atomic number, 92, is equal to 90 plus 2. So we have a balanced equation here for alpha radiation. So what you're going to have to do is you're going to have to recognize all of these different types of radiation by their radioactive equations. So if you see this heavy alpha particle, so a helium nucleus, sometimes you'll also see this written as an alpha term here instead of helium. So alpha looks like this. And so the noteworthy thing is you're going to notice a mass of 4 and an atomic number of 2. That's alpha radiation. The next is beta radiation. So if we take a look at a stream of beta particles coming out, we're going to see that beta particles are repelled by negative charge and attracted to positive charge. They increase the atomic number by 1, but the mass number is unchanged. So based on this information, what are beta particles? So if they're repelled by negative charge and attracted to positive, that means that they are most likely overall negatively charged. If they don't change the mass number, that means they're an extremely light particle. And if they increase an atomic number by 1, that means that it has to be an electron. And so these beta particles are what Thomson used in his cathode ray experiment. So if we take a look at radioactive iodine here, we can see iodine producing xenon plus the release of a beta particle, which is known as an electron. So we can see that we have 0 as our mass number and then a -1 as I described previously for our atomic number. And again, we can see that our mass number for our reactants and products are unchanged, and our atomic number here is also unchanged. So beta radiation, you're going to see this electron present in the products. Gamma radiation is a stream of particles or a stream of energy that is both unaffected by negative charge and positive charge. So we can see the radiation coming straight through. It does not change the atomic number and does not change the mass number. So based on these information, what are gamma rays? So gamma rays are just high energy electromagnetic radiation. So we'll get into electromagnetic radiation in next lecture. But these gamma rays are just a way to release energy upon a radioactive event. And so this gamma radiation always occurs during all radioactive processes. It accompanies alpha and beta radiation both as a mechanism for energy release. And so there's no chemical equation or nuclear equation that explains beta radiation because it doesn't end up changing the mass number or the nucleus itself. So there are 2 other types of radiations that are important to note. One is called positron emission, the other is called electron capture. So positron emission radiation are where a proton changes to a neutron, which decreases the atomic number and ejects what's called a positron. So what a positron is a particle with the same mass as an electron, but at an opposite opposite charge, excuse me. So it can be thought of as a, quote, positive electron. So we see here with this equation here, we have the same sort of shape as an electron here, but instead, or same symbol as an electron, but instead of a negative one, we have a positive one. So it has no mass, but it carries a positive charge. So where do we actually see these positron emission radiation occur? We see them in the medical community when we're talking about PET scans. So PET scans, positron emission topography here, is where we have a positron emitting isotope, such as this fluorine-18, accumulates and emits observable gamma radiation when it hits certain targets. So in this case here, we can see the metastasis of a cancer throughout a body. And so what you can see is that we see this gamma radiation, which accompanies this positron emission radiation, that can indicate the presence of the tumor. And so here we can see the equation of a positron emission radiation. We have radioactive potassium here going to argon, and what we see is a decrease in our overall atomic number, and then the presence of this positron in our products. The final type of radiation we'll talk about is called electron capture radiation. So in this case, the nucleus captures an electron and converts a proton into a neutron. And so in this type of radiation, electrons are the reactants. So here we can see radioactive mercury here, where we have an electron, so E with a 0 mass, and again a -1 charge, says this is an electron. So we have the electron as a reactant. And then we can see that that mercury turns itself into a gold molecule or gold atom. So what we can see here is no change in our mass number, but we have an overall decrease of 1 in our atomic number. Okay, so the important part here is to be able to identify what is happening in each of these sorts of equations for each type of emission. So this table here is just sort of an overview of what each sort of radiation does to a chemical equation. So these are a subset of reactions called nuclear reactions, and they differ from chemical reactions. So if we think back to Dalton's atomic laws, so the theory of Dalton's laws that we went through about a week or so ago, Dalton's laws are that all molecules are made of atoms, that atoms has particular masses, that molecules are made by fixed proportions of atoms combining, and that chemical reactions do not actually change the identity of the atoms themselves, they only change the ways in which they bind to one another, okay, the ratios in which they organize. And so what those are for chemical reactions. So that number 4 of Dalton's law are talking about chemical reactions where we're not actually changing the identity of the atoms, only the way in which they organize. Nuclear reactions are a totally different classification of reaction, where we are actually seeing the change in the specific types of atoms involved in the reaction. So for a nuclear reaction, you see a change in the atom's nucleus to produce a different element, whereas for chemical reactions, you change the way in which atoms are combined. Okay, so that was the 4th of Dalton's laws. For nuclear reactions, products of nuclear reactions behave differently, so there are different elements. Whereas for chemical reactions, different isotopes do not change chemical reactivity. Okay, for example, if you change from uranium to thorium in a nuclear reaction, your reactants and products are not going to act they are going to react drastically different. And so for nuclear reactions, you're going to have very large energy transfers as that gamma radiation is released. And for chemical reactions, typically there's very small energy changes. Okay, so our last slide of the day today is to look at these different types of reactions here and identify each of the reactions as either alpha radiation, beta radiation, positron emission radiation, or electron capture. So I invite you to pause the video and go through and work through those yourself. Okay, so we'll work through these here together now. So we have our decay of tin So SN 126 going to E with a 0 minus 1 plus SB, which is antimony, 126.51. Okay, so what we note here is that we have this particle as a product. And so we need to identify what this particle is. So it's an E with a 0 mass and a minus 1. So what this actually is an electron. So it is an electron as a product. That tells us that this is beta radiation. The next one, if we have radium, 210, 88, having an He42 plus radon 206, 86. Okay, so we identify that we have this particle here, which is a helium nucleus, which is also known as an alpha particle, so that can also be written with an alpha sign there. And so that tells us very clearly that that is alpha radiation. Next, we have our decay of rubidium, Rb, 7737, giving us an E01 plus Kr, 7736, so krypton. Okay, and so what we see here is this particle here, an E with a plus 1, is a positron. And the only type of radiation with positron is positron emission. Finally, our last one here, krypton, 76, 36, plus E0 minus 1, yielding Br35, 76. Okay, and that we have this particle here as a reactant, and we can identify E with a 0 mass as minus 1 as an electron. And so an electron in the reactants means that this is an electron capture. So this molecule here is capturing an electron. Okay, so you should be able to recognize each of these different types of equations, and then you should also be able to, if given the starting material and whatever sort of particle that it either produces or takes up, you should be able to balance the equation and determine what the product is going to be. Okay, so for example, we'll use the same examples here. So if you were given this tin 126 and you said that this underwent beta radiation, okay, you should understand that beta radiation means that there's going to be an electron as one of the products. And we know that our mass number is going to be unchanged, so that means that 126. But we know that these two numbers have to add up together to get to 51. So we know that 51 minus 1 is going to be equal to 50. In that case, we would then look on our periodic table and see which element has a value of 51, an atomic number of 51, and that would lead us to determining that it was antimony. Okay, the same sort of idea if for the next one, if we started with that radon, 210, 88, and if we told you that this went through alpha radiation, you should be able to tell me that we had a helium particle, 42, and so this tells us that a number plus 4 is going to be equal to 210, which would tell us that the value has to be 206. And then a value plus 2 is going to be equal to 88, so that would tell us that 86. And again, we'd look at our periodic table and determine that Rn, radon, would be our value. So you should be able to work through these problems in both ways in order to solve these radiation problems. All right, that's it for the day. Thank you.